Hello, everyone. Thank you very much for coming to our session. We'll talk today about how Google protects your data at rest and in transit. My name is Il-Sung Lee. I'm a product manager in the security and privacy area, specifically working on key management. And I'm here with Maya Kastorowski, who is working on GKE security. She used to be, I guess, what I'm doing now. So she used to own the key management system. I took over for her, so in case you can't tell us apart, she's one with more hair. And so that's the main way you can do it. And I'm also noticing, and this is just basically my OCD-ness, but people like to sit on the edges of the rows. I'm not sure if that's for a quick exit or whatever else, but yeah, probably right. So quick question. How many people here are here to learn more about data at rest as opposed to transit? All right, and how about data in transit? Is that more important? Well, too bad, you're gonna learn both, right? So you're gonna learn about the data at rest and transit today, and I promise you that you'll learn something new, maybe not necessarily in one or other, but hopefully in both. And so when we talk about encryption, right, we usually talk about three broad areas. So you talk about data at rest, which is typically the data that's stored on disk or when you're not using it. Data in transit, when you move it around, right, over networks or from IPsec into process communications, or in use when the data is actually loaded into active memory and it's being used. Now, we're going to cover rest and transit, not so much in use right now. And it's not that I don't want to talk about it in use, but currently right now there's not a lot of great industry solutions around this. And so the rest and transit are very, very mature type of technologies. Now, when we start talking about encryption at rest, you got to kind of think about how enterprises approach encryption. So this picture kind of depicts different types of customers or enterprise customers. So you may have small customers who basically probably don't have a lot of need for maybe key management. Maybe they are looking to actually use a default solution that the cloud provider provides them. And that's sort of like service A. They basically take the encryption mechanism that's provided with whatever is provided to them. And as they get a little bit bigger, they may decide that, hey, I want to do my own key management, right? I have more complex scenarios, I have more data, I have different keys I need to use. And so I may actually have either my own key management system, off the shelf, whatever is available. And we use that, right? And then you get to maybe service C. And this is where you're talking about the very large corporations. They've got lots and lots of keys, right? And so when you have lots of keys, then you have to do a lot of key management. And when you do a lot of key management, things get pretty complex, and they may have custom solutions to handle this. In addition to actually just using the keys to actually be stored in the KMS, they may also use something called an HSM, or hardware security module. And how many people here know what an HSM is? Wow, that's amazing. You guys are in the right class. So they use HSMs because it provides some levels of assurance around compliance, security, things like that. And that makes them feel really, really good. Now, when we start talking about the Google Cloud, and one thing I always like to mention to everyone and make sure everyone's aware is that when you put your data up into our cloud, we always encrypt it. There's no such thing as unencrypted data at rest, right? And it's nothing that you can turn off or do anything like that. It's just something that we do, and there's no choice around it. Now, the data gets uploaded to Google, and what we do is we go through this very elaborate process to actually protect your data in several different ways. The first thing we do is that we take the data and we break it up into small chunks. You can think of them as shards or blocks or whatever you want to think of, but they're broken up into small chunks, and for each of those chunks, we generate a random, unique AES key. Okay? And so you may ask, why do you do that? Well, it's obvious. One of the obvious reasons is that it reduces the blast radius. So if one of these keys gets compromised, then you don't lose all your data. You lose a small fragment of it. And in order to actually get access to the complete set of data, you have to actually be able to break all these different keys, which is actually not a trivial thing to do, right? And so each chunk of data gets its own encrypted key, and this encrypted chunks of data gets kind of distributed throughout the data center. Okay, they get replicated and they get moved around, and so again, this is also helps from a security perspective. A lost hard drive is likely not going to lead to anything catastrophic, right? Your data is not all collectively put in one place. It's broken up and distributed across the data center. And our data center has many, 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 many servers, right? Lots and lots. And so that's what happens there. Now, when you start talking about encryption, then it's not the actual process of doing encryption that's hard. It's the key management, right? Everybody knows this. I mean, protecting keys is a very, very hard thing to do. And because no matter how good your encryption is, if someone takes a key, then they access your data. As simple as that. In our case, what we do is that when you actually have that piece of data, we create this new key that's associated with it. Now, that key actually stays with the data itself, and you obviously don't want to do that in plain text, because then it's even stupider than unencrypting. But we then wrap it, we encrypt it using a higher level key that we call the key encryption key. So it makes sense, right? Data encryption key for the data, and then key encryption key for encrypting the data. The key, I'm sorry. And the way that this works is that the key encryption key resides in our own internal key management system. And this key management system was designed to be very highly scalable, available, everything else. It's basically what we use internally to run Google as well, right? So it had to be something that can perform well enough to support the entire Google domain. When the key actually gets protected in there, then the cloud KMS and the internal KMS also has properties by which it actually makes sure that the proper ACLs are involved. Like the services have the proper access to actually access key for this particular data. And I'll talk a little bit more about that as well. But let's kind of walk through what happens when a service accesses an encrypted piece of data. So first thing that happens is that you have three parties here, right? You have the service, the storage system, and the actual key management system. They all have to work together to make things work. The service comes in and says that, hey, I want this piece of data. Please give it to me. And so what the storage system does is that, first of all, it checks, does the person actually have access to this data, right? And if it passes that IAM check, then it says, OK, let me go and figure out how to do this. It will go and figure out which chunks collectively form that data. And then each of those chunks will actually have its data encryption key sent over to the KMS to actually go and decrypt, right? So that it can actually decrypt the data. So it does that for each of the different chunks. And then once it gets back the unwrapped data encryption key, it can then actually put the data back together and then send it back to the application. Well, I should mention, too, if you guys have any questions, please feel free to interrupt. I'd rather ask right now. Yes, please.
You said everything's encrypted at rest, but in the documentation it says there's some exceptions like console logs.
Yeah. So the question is that, I said that all data is encrypted at rest, but there's documentation of some things that are exceptions. So I should clarify, when I say data, I mean customer data. We make a distinction between customer data and metadata. And things like logs and information around the data is considered metadata, which we don't necessarily ensure they're encrypted.
Well, console logs, if you have an application that sends something to the console, it shouldn't be, but that would be.
That's true, but we try to make sure that there's nothing in terms of sensitive data that's actually placed into these logs, right? Now, if you actually do something where you actually, name certain objects with the sensitive information, we advise you not to do that. But again, we make that distinction. And so you're right, but we cannot always encrypt the metadata for various reasons. Okay. So now we get down to a little bit more in terms of the key hierarchy. And so this diagram here actually gives you a fairly good picture of how we do protect the keys within the storage system. And so once we actually get to the top, we've already discussed that, where they have the keys encrypted, and the internal KMS actually is protecting the green keys there. It goes through a whole elaborate system of different keys that actually protect it, through different layers, to the point where at the second from the bottom right there, you end up with a root KMS master key. And this is a key that runs on very, very special machines, very highly secured machines in each of the data centers. There's not very many of them. Okay, they're designed to be very, very reliable and performant and everything else. And they are also meant to not store the keys on any permanent media. Okay, so they only exist in memory. And there's an internal protocol that actually shares the keys around. So as long as you have one of these machines running globally, then it'll be able to recover in case any of these machines die. Now, in the case where we have a catastrophic failure, like everything goes down, like a global reset, then we do actually keep a hard copy of that key. We put into a physically secure media and lock them into a physical safe that's distributed in a globally disparate set of locations around the world. And there are very, very few people in Google that actually have access or knowledge of this. I'm definitely not one of them. I'm not considered trustworthy enough. But there's probably less than 20, if I remember correctly. Okay. Now, just as a kind of general statement that I'll make around this is that, the way we can describe encryption at rest by default is that Google encrypts customer content stored at rest without any action required from the customer using one or more encryption mechanisms. Okay. So what I described right there is one of the mechanisms that we use to actually encrypt your data. There's sometimes more at the physical layer and everything else, but you can rest assured that there's at least, your data has been encrypted at least once. Yes?
At some point, you instantiate that key load into memory with a bootstrapping system. Can you go into how you did that on the
So the question is how do we instantiate the key that's bootstrapped into memory, right? So again, as long as one of these nodes are up, and so you have these specialized nodes that only actually serve to actually provide this hostess root KMS master key. So there's basically a sharing protocol that's inherent with the system itself. And so they know how to actually contact one another to actually make sure that the key gets shared and propagated throughout the system. And so if there's a new machine that comes up, then it automatically gets shared with the brand new key. It's a little bit more elaborate than that. I can't get into too much more details, but yes.
initially, there was no key material. When you initially instantiate that first node, do you know the process?
Oh, I see. So when you start from zero and you actually want to I'm not sure about that, to be quite honest. I imagine that there's some process by which the few people who know how to do this would set up and get started, but I'm not exactly sure. Yes, question?
By the way, when you retrieve the data from one of the servers, what is the traceability from each server that they retrieve basically?
I'm sorry, could you repeat that?
You said that there is a unique ID, matching between the different pieces of data, right?
Yes.
Okay. That means that on whole there is a traceability of where these pieces of ID came from.
Oh, I see. So the question is basically around traceability of where the data resided. Yes, there's both internal logs that actually keep track of all the activity that happens in terms of key management, key access and everything else. And then at a higher level, there's also the cloud auto logging that would actually that's not for this case, but there is actually logging that actually keeps track of the different accesses and the different key requests and everything else. So that is all, that's all actually recorded in our internal logs. Okay. I'm sorry? Will it appear in the metadata? Like, do you mean if someone accesses the metadata? Yeah, there would be logs in case that any key access, right. But it's not necessarily something that's exposed externally. Going forward here, so now we actually get to the point where we're starting to talk about things that you can manage yourself. So this is options for encryption at rest. And so when you actually bring up, like your data to the cloud, we discussed the first column there, which is a default encryption, where you can actually go and do nothing, and we'll just make sure all your data is encrypted. And then in the middle, we have the customer managed encryption keys with Cloud KMS, right? And that's the case where Cloud KMS is the cloud service that's sort of the external instantiation of the key management system. And one of the great benefits of the KMS is that you can actually have this integrated to protect with different services. So currently, I'll talk a little bit more about this, but if your data resides in other services, then you can actually associate with a key that you control under Cloud KMS. And then finally, on the right side, we have customer-supplied encryption keys. And so this is a feature that we shipped a couple years ago. And this allows you to actually, it's only available for GCS and GCE, I should mention as well. But this allows you to actually, keep the keys resident, so you don't store them in the cloud. But every time you actually make a call that needs to access data, you actually provide a secret that helps unlock that data. Now, that secret is something that we actually only keep in memory. We don't actually store to disk ever. And so as soon as you finish a request, we actually purge it, right? So it's only for GCS and GC, as I mentioned before. It does have some drawbacks, such as you can't do anything that's offline, or like for example, we can't do any kind of backups or things like compaction and things like that. So it kind of limits what we can do with it in terms of the different services. Okay. Now I'll talk really quickly about Cloud KMS since I mentioned it earlier. So Cloud KMS is actually the external key management system, and this is all taken from the website, so I won't spend too much time on this, right? But it basically gives you a path by which you can actually go and create AES-256 keys, and you can manage them yourselves, right? You can explicitly say that I want to create, destroy, rotate, disable, whatever you like with this. And it's because it's a cloud service, it's completely integrated with Cloud IAM and Cloud Autologging. So that means that you can actually use IAM roles to actually dictate who can access the key and what operations they can do. And in addition, all the operations will be captured by Cloud Autologging. So whenever someone goes and accesses the keys for whatever operation, then that will be something that's captured by the log. Okay. This is just basically describing some of the things that, if you're familiar with Cloud KMS, you already know. But it's designed to be a global, scalable performance system. It's extremely fast, very, very low overhead. Just because the way that it works is that there's many KMS nodes that do a lot of the work, and so it means that when you actually do encryption, it actually doesn't really meaningfully impact the performance of the system. And then this is something that that's probably interesting to a lot of people. What's new? Asymmetric keys. We're finally introducing asymmetric keys for Cloud KMS. Okay, so the other slide, a couple slides ago, I said it does symmetric key. That was the case until this morning. We just announced that we're providing Cloud HSM, and along with Cloud HSM, we're also providing the ability for you to actually go and do asymmetric key operations on both hardware and software. And we're allowing you to do several different types of keys. Okay, so you can actually use RSA 2K, 3K, and 4K. You can use that both for signing, and you can use that for decryption. And then we'll also provide you with elliptic curve keys with a couple of the NIST curves, P256 and 384. So you can use those for signing purposes. We've also expanded since last year to multiple regions. So very recently, we expanded to Finland, London, Frankfurt, Netherlands, and then Tokyo, Mumbai, Sydney, Montreal, LA, and Sao Paulo. Okay. Another thing that's really cool is that we are now supporting multi-regions. So if you're familiar, we had a multi-region before, but it was one multi-region. It was global, right? So either you chose a specific region or you chose the whole entire world. And for some reason, some people didn't like that. So we're providing you with the ability to actually choose individual regions. So you can either choose the Europe, Asia, or US multi-regions. Okay? And it's just basically a very, very simple thing when you create the key ring. And finally, I just mentioned this a little while ago, but we're providing HSM backing for Cloud KMS. Okay, so this is a very, very fantastic news. I've been working very hard on this for the last couple of years. So it's been my life for a little while, so I feel very, very happy and sad at the same time. But it's basically a managed HSM service that allows you to actually go and do crypto operations, create protection of your keys, in a FIPS 140-2 level 3 device. And if you think that's going to be hard to manage, well, you don't have to do anything except know how to use Cloud KMS. And it's just a simple flag when you create it. You say, I want to create this in HSM. And we just take care of the rest for you, essentially. Okay? It's an HSM, which means that when you create the keys in there, we can't extract the key material. Okay? We actually really don't have the capabilities of actually doing it. And the keys are actually bound to a region itself. When you create the keys in, say, US Central 1, then the HSM hardware in US Central 1 is a thing that binds and creates and binds the keys to that region. So even if the key backup gets moved around, it can't be used anywhere else. Okay. I have a whole session on this tomorrow at 10:20. And so if you're interested about this, please drop by. I'll talk a lot more about the HSM stuff and do a lot more demos and stuff like that where you can see how it works. Okay. All right, I see people taking pictures, so 3, 2, 1, okay. And finally, customer managed encryption keys. If you guys haven't used this yet, you should really consider it. It's great. It essentially allows you to use the encryption that we provide into the different services but protect it using a key that you control in Cloud KMS, right? And because Cloud HSM is integrated with Cloud KMS, you can also use an HSM key as well if you feel like having some tighter controls around the availability of the keys. And so currently right now, we have this available for BigQuery. That's fully GA. The compute engine, cloud storage, Dataproc, they're all in beta right now. And so you're free to try this out with both software and hardware keys. There's a talk released for the GCS happening tomorrow, Thursday at 10:20 a.m., same time. I hear the HSM talk is a little bit better, but if you're interested in GCS, then please feel free to actually go and attend this session, learn a little bit more. I don't think they're going to talk exclusively about this, but they'll mention it. And with that, I think I'm going to turn it over to my predecessor, Maya. So here you go, Maya.
Thanks, Ilsung. Oh no, no, my microphone first. Okay.
Can't have nice things.
I put it in my pocket. Still work? Can you hear me? Did I turn it off? We're good? Great. Thanks, Ilsung. Unfortunately, I'm not as funny as Ilsung. I'm sorry in advance, and also I talk very fast. So we'll see how this goes. So the other thing, in case you missed some of the announcements that Ilsung mentioned, go check out the blog. We posted all the security announcements a couple hours ago, including Cloud HSM, if you're not familiar with that. So I'll be talking about encryption in transit at Google and how that works. So if you're not familiar and to understand how encryption in transit works at Google, we first need to understand how traffic moves to Google and then inside Google. So there are 5 kinds of different routing requests here. They're numbered on the slide. From the end user to a Google service, from the end user to a custom application hosted on Google, from a virtual machine to a Google service, from a virtual machine to another virtual machine, and from a service to another service. So the distinction here, a service is a hosted service like a BigQuery or CloudML, et cetera, versus a VM is a VM endpoint, has an IP address like GCE, GKE, or a Google managed VM like Cloud SQL is. So number 1 here, from the end user to a Google Cloud service. For example, if a user is connecting to BigQuery to run a query, Google Cloud Services accept requests from around the world using a globally distributed system called the Google Front End, or GFE. And the GFE will terminate incoming HTTPS, TCP, and TLS proxy traffic, provide DDoS attack countermeasures, and route and load balance traffic to the right Google Cloud service. There are GFE points of presence around the globe. So they proxy that traffic internally by writing the user's request over our network backbone to the right spot. 2, from the end user to a customer application hosted on Google Cloud. This is actually the most complicated case, so hopefully we don't have to, I can talk through some of the examples that you have. So this depends on how your traffic is routed through the internet to your customer application. If you're using a Google Cloud load balancer, you can use it to terminate HTTPS, TLS, and TCP traffic. And it's actually implemented by the GFEs. So that's why you have the same parallel set of options there. For HTTPS load balancers, connections between end users are encrypted and authenticated with TLS or QUIC using certificates that you provide. Some other options, if you're connecting using Cloud VPN, you connect from your host, on your VM on premises to the on-prem VPN, to the Cloud VPN, to the Cloud VPN. And the connection between the 2 VPNs is protected using IPsec. And we'll talk a little bit more about that. If you're connecting directly to an external IP for a VM, that connection does not go through the GFE, and it is not encrypted and protected the same way that a connection to the GFE is. So if you're serving something directly from an IP endpoint, that's your responsibility to protect and encrypt that traffic. Similarly, if you're using cloud-dedicated interconnect, for example, to peer between your on-premises and Google Cloud, that also does not go through the GFE, and so it's also your responsibility to protect that, for example, by implementing some application layer encryption. From a virtual machine, so those 2. For 3, from a virtual machine to a Google Cloud service, it actually just reduces to another case, which is it will connect to a GFE. We will route that request, for example, from a compute engine VM to Google Cloud Storage, as if it were an external request and get sent to the GFE. Then GFE will then do their load balancing and routing internally for that. From a virtual machine to a virtual machine, that connects over our network backbone using private ROC 1918 IP addresses. And from a Google Cloud service to another Google Cloud service also goes over our private network backbone. We'll talk a little bit about what we do for both of those in a second. So here we go. To get us started here, our networking team is amazing, and all the stuff that you saw there was kind of crazy, but I'm a security person, so I care about how that traffic is protected. All those 5 different things are protected. So First, from the user to the front end, it travels over the open internet, and then I'll talk more about how we protect that in a second. Then once your traffic is inside Google's infrastructure, your data travels over our private network backbone and might go to multiple physical locations in order to fulfill that request. So how is our network backbone protected? It's really important here to understand that Google applies different protections to data in transit when it's transmitted outside of a physical boundary controlled by or on behalf of Google compared to when it stays inside Google's physical boundaries. So what do I mean by this? A physical boundary is the barrier to a physical space that is controlled by or on behalf of Google, where we can ensure that there are rigorous security measures in place. Physical access to these locations is restricted and heavily monitored. Only a small percentage of Google employees can have access to that hardware. And because we tightly control that space, data in transit within these physical boundaries is generally authenticated, but is not necessarily encrypted. Now, compare that to the scale of the global internet, or everything in our wide area network. We just can't put the same physical security controls in place, right? We can't put like a Google employee standing every 10 feet of some fiber optic cable under the sea, making sure that that's all secured. So anywhere outside our physical boundaries where we can't control that link, we assume that any network crossing a physical boundary can be compromised by an active adversary who could snoop, inject, or alter traffic on that wire. In order to ensure data integrity and privacy, we use encryption when data moves outside physical boundaries. So those undersea network cables, encrypted. I want to repeat this because it's really the key takeaway here before I get into details. Based on our threat model, Google encrypts and authenticates data in transit when that data moves outside physical boundaries, but whereas data within a physical boundary is generally authenticated but not always encrypted. All right, so now that we have the high-level picture, let's talk through some of the different scenarios, both to the Google front end and then within Google's infrastructure at multiple network layers. So as I mentioned briefly earlier, your data can travel from the user to the front end in a few different ways. Let's take the most simple case where it talks where you're a user and you connect to a Google Cloud service. So in this case, the Google front end, like I mentioned, will terminate your connection and provide encryption using HTTPS protocol with a public certificate. The GFE will negotiate a particular encryption protocol with the client depending on what the client's able to support. The GFE will negotiate a more modern encryption protocol where possible. TLS in the GFE is implemented using Boring SSL, which is a Google-maintained open-source implementation of the TLS protocol, forked from OpenSSL, and is mostly interface compatible with OpenSSL. Google's an industry leader in both the adoption of TLS and the strengthening of its implementation. We've enabled many of the security features of TLS. For example, since 2011, we have been using forward secrecy in our TLS implementation. Forward secrecy makes sure that the key that protects a particular connection is not persisted, so that if that connection is compromised, if an attacker can intercept a particular message, they can't read previous messages that you sent over the same connection. As part of TLS, a server must prove its identity to the user when it receives a connection request by having the server present a certificate containing its claimed identity. This certificate is signed by an issuing certificate authority, or CA, that's trusted by the user requesting the encryption. Historically, Google operated its own issuing CA, which is what gives you the certificates. And we use these to sign certificates for Google domains. But recently, Google's also started operating our own root CA. So the root CAs sign the other smaller CAs that operate across the internet. Today, our CAs serve certificates that are cross-signed by multiple roots, which are ubiquitously distributed. So to summarize, when you connect to Google, the Google front end terminates your traffic, encryption is implemented using Boring SSL, and certificates are cross-signed, including by Google-owned root CAs. Now, let's get into our network. Now that your request is inside Google's infrastructure, I might have to travel between Google locations. We have protections in place both at the network layer and at the application layer. Let's start at the network layer. At this layer, Google Cloud's virtual network authenticates all traffic between virtual machines. This authentication is implemented using a system that we call security tokens, which protect a compromised host from spoofing packets on the network. Security tokens are HMACs, negotiated for a given sender and receiver pair. So a sender VM and a receiver VM will each have their own set of tokens. During authentication, security tokens are encapsulated in a tunnel header which contains authentication information about the sender and the receiver. The control plane on the serving side sets the token, and the receiving host validates the token. Furthermore, Google Cloud's virtual network infrastructure enables encryption when traffic goes outside physical boundaries, like I was saying before. Encryption applies to private IP traffic within the same virtual private cloud or between peered VPC networks. we use the advanced encryption standard in Galois counter mode with a 128-bit key to implement encryption at the network layer. Each pair of communicating hosts establishes a session key via a control channel protected by ALTS, which I'll talk about in a second, for authenticated and encrypted communications. The session key is used to encrypt all VM-to-VM communication between these hosts. Going up to the application layer, the protection story is very similar, although the implementation is different. At the application layer, within Google's infrastructure, we use Application Layer Transport Security, or ALTS, for the authentication, integrity, and encryption of Google RPC calls. This includes RPC calls from the GFE to a service and from a service to another service. ALTS uses service accounts for authentication. Each service that runs in Google's infrastructure has a service account identity with associated cryptographic credentials, which it can use for authenticating itself to other services. When making or receiving RPCs from other services, it uses that service account to authenticate itself, to provide its credentials. ALTS will verify these credentials using an internal certificate authority. Within a physical boundary controlled by Google, ALTS provides both authentication and integrity for RPCs. For traffic over the WAN outside of physical boundaries, ALTS furthermore enforces encryption for infrastructure RPC traffic automatically. ALTS is also used to encapsulate other layer 7 protocols, such as HTTP. This protection ensures that this isolates the application layer and removes any dependency on the network path. Services can also be configured to only accept and send ALTS communication when encrypted, even within physical boundaries. Notable examples within Google are our internal key management system that Ilsung was describing earlier, and Cloud KMS, both of which only accept encrypted communications. Let's dig a little bit deeper into how ALTS works. Google's Application Layer Transport Security, or ALTS, is a mutual authentication and transport encryption system developed by Google, and typically used for securing remote procedure communications, or RPCs, within our infrastructure. ALTS is similar in concept to mutual TLS, if you're familiar with how that works, or any handshake protocol, really, but has been designed and optimized to meet the needs of Google's data center environments. The ALTS trust model was purpose-built for cloud-like containerized applications. This is a key point. Identities are bound to entities, like a service account, not bound to a specific server name or host, like an IP address. This trust model makes it really easy for us to replicate, load balance, and reschedule microservices across hosts. Sounds a lot like Istio. ALTS relies on two protocols: the handshake protocol to establish a session key, which you see at the top there, and a second protocol, the record protocol, to send the protected RPC. These protocols govern how sessions are established, authenticated, encrypted, and resumed. So first, the handshake protocol. It's a Diffie-Hellman-based authentication key exchange that supports both perfect word secrecy and session resumption. During a handshake, the client and the server will negotiate a shared transit encryption key and the specific protocol that they're going to use for encryption. And then the record protocol sends the data, encrypts and authenticates network traffic using the protocol secret that was established in the handshake. We've published a white paper explaining exactly how ALTS works on our website, so please do check that out if you're interested. So let's summarize what we've seen so far. And apologies for these being on two different slides. So first, what happens at layer 3, at the network layer? We've covered what protections we have in place by default. We mentioned that we have virtual network authentication between the GFE to the VM and between VMs, and we have encryption when that data crosses physical boundaries. I also want to point out, it's not that we don't have any protection from the user to the front end or from the user to VM, but that's not at layer 3, that's at layer 7. So I get asked often, is there any point where my data isn't encrypted in transit? What are my options? What can I do? At this network layer, in addition to this protection that we already have, if you need additional protection from the user to the VM or between VMs, you can use an IPsec tunnel. How do you set that up? You can use Cloud VPN to set up an IPsec tunnel to securely connect your on-premises network to your Google Cloud VPC. You have the option of setting up you can also set up a VPN between two VPCs. This means that your traffic would go from your on-prem host to your on-prem VM to the cloud VPN, from your on-prem host to your on-prem VPN to your cloud VPN to your cloud VM. So there's 3 hops there that it's making, right? From your on-prem host to your on-prem VPN, that's on your network. It's protected like you would protect any other traffic in your environment. From the on-premises VPN to the cloud VPN, that's protected using an IPsec tunnel. And from the cloud VPN to the cloud VM, that's protected by our virtual network, as we previously explained. So to set up a VPN, you first have to set up a VPN on premises. Then you can create a cloud VPN gateway and tunnel on the hosted service's VPC network and permit traffic between the networks. You can further customize your network by specifying the Internet Key Exchange version for your VPN tunnel, IKEv1 and IKEv2, each of which supports different ciphers. If you specify IKEv1, Google will encrypt the packets using AES Advanced Encryption Standard in cipher blockchaining mode with a 128-bit key, and provides integrity using a SHA-1 HMAC. If you're using IKEv2, you have a variety of ciphers that are available to you and supported. And in all cases, Google Cloud VPN will negotiate the most secure option available between the peer devices. An alternative to an IPsec tunnel I mentioned briefly earlier would be to use something like Google Cloud Dedicated Interconnect to connect from your on-premises to Google Cloud. In that case, it provides direct physical connections using RFC 1918 addresses between your network and Google's network. The data traveling over this connection is not encrypted by default, and it's your protection to secure this. It's your responsibility to secure this, and we'd recommend, for example, application layer encryption, for example, using TLS. So that was at the network level. Let's look up at the application layer again. As you recall, we use TLS to encrypt data from the user to the Google front end, and also from a VM to the Google front end, because that's how we route traffic back through the GFE. And then we use ALTS within Google's infrastructure between services for authentication, integrity, and furthermore, encryption between physical locations. To avoid confusion, I also want to point out here that VM to VM traffic, it's not that it's not protected. Again, it's protected at layer 3. If you need additional network layer protections from the user to the GFE, we have a couple of different options, including managed SSL certificates for your user applications. And in Gmail, you can use MIME. And within Google's infrastructure, if you need additional service-to-service protections, you can use Istio. So let's quickly dive into what these provide. When building an application on Google Cloud, you can leverage the GFE support of TLS by configuring the SSL certificate that you want to use. For example, you could have the TLS session terminate in your application. As well, Google provides free and automated SSL certificates in both Firebase hosting and Google App Engine custom domains. These certificates are only available for Google-hosted properties. Once your domain is pointed at Google's infrastructure, we request one and obtain a certificate for that domain to allow secure communications. We manage this TLS server private keys on your behalf, which are either 2048-bit RSA or SecP 256 R1 ECC, and renew certificates on your behalf as well. For Gmail specifically, Gmail already uses TLS by default. So in fact, Gmail actually records and displays whether the last hop that an email made was over a TLS session. When a Gmail user exchanges an email with another Gmail user, the emails are protected by TLS, with the exception of if they're sent directly within the application, they're protected with ALTS, as we described earlier. For incoming messages from other email providers, Gmail doesn't enforce the use of TLS. If this is a requirement for you, as a Gmail admin, you can go configure Gmail to require a secure TLS connection for all incoming and outgoing emails. If you have stronger enterprise requirements for secure multipurpose internet mail extensions, or SMIME, which is an email security standard that provides authentication, integrity, and encryption for your emails, then you can implement that in Gmail as well. The implementation of SMIME standard mandates that certificates associated with users sending emails are hosted in a public CA. If you have this requirement, as a Gmail admin, you can configure Gmail to enable SMIME for outgoing emails, set up policies for content and attachment compliance, and create routing rules for incoming and outgoing emails. The last additional protection we'll quickly cover is Istio. Istio is an open source service mesh that provides a uniform way to connect, monitor, and secure services. The trend towards microservices and containerization in general is leading to more complicated applications that are more difficult to monitor, and why I'm excited about container security these days. Sorry, Ilsung. Istio supports managing traffic flows between microservices, enforcing access policies, and aggregating telemetry data, and all of that without having to change your application. So it's a complete godsend in that regard. Given Google's experience with ALTS, Istio is a logical extension of what we've already built and what we've done in developing microservices for over 15 years. Like ALTS, Istio issues an identity, which is a certificate, for every service running in the mesh. Istio then transparently adds mutual TLS to all service calls based on these identities, providing authentication and encryption across your services. There are lots of talks at this conference on Istio, so I won't dig into it. There was one yesterday on Istio security, so check out that recording online. So to sum it all up, for data encryption in transit, Google encrypts and authenticates data in transit at one or more network layers, the network layer and the application layer, when data moves outside physical boundaries not controlled by or on behalf of Google. And if you want to learn more, I've spent some large amount of my career writing niche white papers. You can go check them out. Learn more about encryption in transit, encryption at rest, what Ilsung and I talked about today. Thank you so much for your time.